I think we can start now since it's 7. Is that good? Yeah. Okay. Can I request all the speakers to put themselves on mute and put it on whenever you're speaking? So good morning to those in US and other time zones, and good evening to all in India. It's a pleasure to welcome all of you for this webinar on deploying cost-effective battery energy storage system into the Indian power grid. We are delighted to have all of you join us for this particular webinar. This webinar is being organized under USAID's bilateral program with the Ministry of Power called Greening the Grid RISE initiative, RISE standing for Renewable, Integration and Sustainable Energy. This is a bilateral program with the Ministry of Power with the aim or objective to support large-scale integration of renewable energy. And as a part of this program, we have been doing a lot of, a series of pilots, grid integration pilots that could help support, integration of renewable energy. And one of the pilots which we are doing is on battery energy storage system. And today we are presenting to you some of the highlights from that particular pilot, as well as, bringing in the expertise which we have within our experts, specifically from DNV, to present to you some international case studies in terms of what's happening internationally in terms of deployment of battery energy storage system. So without further ado, I will now call upon Michael Satin, Director, Clean Energy and Environment Office, USAID India, to make his opening remarks. Michael is a senior Foreign Service officer with several years of experience in energy, agriculture, and other fields. So Michael, over to you. Michael, you're on mute.
Okay, Monali, thank you very much. Thank you to really the entire spectrum of folks who have joined us this evening. It is an honor and a privilege for me to be here, but certainly more importantly, we are grateful for all the numbers of people who have turned out. The issues that we're bringing up and the pieces of technical capacity that we're discussing are no less than technological revolution. It is certainly the case that what we're talking about is transforming the power sector landscape, not just here in India, but around the world. What is really exciting to see is the degree to which India is a leader in this transformation. It's a pleasure for me, as always, to be back on a webinar hosted by USAID's Greening the Grid RISE initiative. I was just on another webinar about 2 weeks back, organized by the team, which focused on the low load or flexible operations of coal plants, also to support large-scale integration of renewable energy. I like to think of our GTG-RISE program as being somewhat of a technical and economic laboratory here in India that allows us to take a look at the phenomenon that will change the power sector and change the landscape of the Indian economy and the social elements of that economy as well. Today, I'm happy to participate in yet another very relevant webinar organized by our RISE team, focusing this time on the battery energy storage systems. This is a key technology that could bring a paradigm shift in addressing challenges related to the integration of renewable energy. Don't need to tell folks here in the audience today the importance of establishing a basis, a technology for storing renewable energies such as solar or wind or hydro, to being able to fully exploit those new and renewable energy resources in the future. Maximizing the benefits of collecting those energy sources, but then being able to use them for some of the things that are absolutely necessary. Social services delivery. The phenomenon we find ourselves in right now, the COVID-19 pandemic, is a perfect example of how our world can be shocked by a number of different phenomena: natural, economic, social, political, and how we as a society need to build a sense of resilience so that these shocks don't destabilize us so much that we can't recover from them. In fact, we need to make sure that recovering from these shocks, we come back stronger. I'm very delighted, as always, to be working very hand in hand with Mr. Anil Kumar, the Joint Secretary for Hydro at the Ministry of Power, the Government of India, who joins us for this webinar. Mr. Kumar, thank you very much for joining us today. Your leadership is always a pleasure to have, and we're grateful for you being one of the critical thought leaders in this area. Today's webinar, Deploying Cost-Effective Battery Energy Storage Systems, or BESS, in India, is organized under a joint program between USAID and the Ministry of Power called Greening the Grid, or G2G as we like to say. The central component of G2G is the Renewable Integration of Sustainable Energy, or RISE initiative, which is piloting a range of technologies and solutions in India to support renewable energy integration. One of the key pilots under the program focuses on evaluating the use and value of these battery energy storage systems, or the BESS, at the transmission level. And we've partnered with the Power Grid Corporation of India Limited, PGCIL, to evaluate the techno-economic value of BESS for providing grid support services at the transmission level specifically. While not directly related to today's webinar, I also want to mention, I think I'd be remiss if I didn't, mention that USAID is also partnering with the BSES Rajdhani, a Delhi-based distribution utility, to evaluate value of battery energy storage systems at the distribution level. So we see the power sector revolution and the transformation as being very comprehensive. Energy sources are not standalone. Generators are certainly not standalone. Transmission operators are not standalone, and certainly distribution or utility operators are not standalone. These are all part of an integrated system. And to understand how new and emerging technologies, management practices, socioeconomic models affect any one of these, you need to understand how it affects each and every one and all of them comprehensively. And our goal is to try and understand that. We've been incredibly successful thus far, and we are excited about going forward with the Ministry of Power and other partners in the government and in private sector to really help achieve some of the outcomes that we're hoping we do. Globally, rapidly increasing portfolios of renewable energy across the world and introduction of these new technologies such as electric vehicles and the BESS system are leading to the transformation of the electricity sector. In this transition, policymakers, regulators face questions such as cost effectiveness, return on investments, potential risks, safety and quality standards to some of the emerging technologies and the solutions. India may also grapple with many such questions as it develops energy storage ecosystem in this country. But in today's webinar, we have senior grid integration advisors from G2G-RISE present, international experience of deploying cost-effective grid storage systems. The experts will touch upon topics such as designing cost-effective storage, the policy and market framework, standards for storage safety systems. We're hopeful that the insights and the learning shared by these experts provide lessons for the Indian power sector. I'm sure we would soon be able to share our experiences from our pilot with the power grid. I will, however, take this opportunity to thank them for their support and collaboration and for partnering with USAID on the BESS pilot. I would like to particularly acknowledge that Dr. Subir Sen, the Chief Operating Officer, and Mr. Manish Tiwari from Power Grid for their guidance, support, and active participation in G2G-RISE. They've been key interlocutors, key advisors, and top-notch conseillers that have really helped us to move this forward in an accelerated fashion and take a lot of good lessons learned home from the work we're doing together. Mr. Kumar, thanks for taking time to join us today as well as for your support of this bilateral effort in the power sector. I want to congratulate the team from Deloitte LLP, implementing partner for G2G-RISE, and the folks at DNVGL for organizing this webinar on such a timely topic. I'd also like to thank the experts, including Dr. Lahiri Sweta and Sharanshu, for sharing their experiences with us today. I encourage all the delegates to take advantage of the vast experience available with these experts and absorb as much as you can. You're going to hear from a number of people who have been the pioneers in this field, who are leading this transformation. We've been very fortunate to assemble them in this particular webinar today. It's an opportunity for all of us to work together to share experiences, to learn from one another, and to learn from these very highly experienced and coveted experts. I do want to, if you don't mind and indulge me, to just take a moment and thank my colleague, Monali Zea, who has really been at the forefront of leading this effort. She is the, as I like to say, the laboratory director of what we're doing at USAID with the Ministry of Power, and is really the thought leader and the sort of critical thinker on a lot of the work we're doing and how we are able to bring these pieces of information to a broader audience, such as yourself. So with that, let me say thank you to all of you for being with us today and for participating and taking full advantage of the information that's going to be shared. Let me wish you the best in your discussions. Let me finally say that in this incredibly quasi-crisis moment in our lifetimes, when we recognize that things aren't always as simple as we'd like them to be, that in fact there are forces in the universe beyond our control often, and we're desperately looking for solutions to the pandemic. Those of us who are working in on the margins of the pandemic and continuing to try and find solutions and solve the problems of everyday life, we are helping India and the world to build resilience, to build that capacity that allows us to face these shocks and come back from these shocks in a way that makes us stronger in the future. I believe the investments that we're making today in BESS, the other investments we're making in how to integrate large renewable energy into our power grid, that these are all part of building a social resilience that will help us not just be okay at the end of these disasters, but be better, be stronger, allow us to bring our economies back when we have to, allow us to seek out and use the social services like education and healthcare for our children and our family and our elder people, so that we can make sure that we don't get put under by any of these things in a phenomenal way, but in fact, we recover and we go on to become stronger as individuals, stronger as families and communities, and stronger as society. So with that, thank you very much. I wish you all the best in this discussion today, and I'll turn it back over to Monali.
Thank you so much, Michael. Thanks for the opening remarks. I would now request Mr. Anil Kumar, the Joint Secretary Hydro at Ministry of Power, to give his remarks as well. Mr. Kumar has been in the sector for a very long time with over 32 years of experience. He was also handling the thermal portfolio at Ministry of Power at one point of time. So, sir, your remarks, your experience would be really insightful for all the audience. So, over to you, sir.
Thank you, Monali, and good evening to all my friends in India, and good morning to all my friends in US. Actually, when I registered for the webinar, I did not have any intention to speak. I wanted to learn. I wanted to listen and learn. But now you have asked me to speak. I'll make some remarks. You see that India is one of the fastest growing economy in the world, and so is our power demand. Our power demand is growing at the rate of 5 to 6%. And as per the estimates and studies done by the Central Electricity Authority, the peak demand is likely to reach 340 gigawatt by 2030, and our energy consumption will rise to almost 2,400 billion units, which is at present 1,300 billion units. But we have decided to follow the low carbon pathways. That is why we are going very aggressively for installation of more and more renewable capacity. We already have almost 85 gigawatt of renewable capacity today, but we have targeted to reach 440 gigawatt of solar plus wind by 2030. But that will have its own problem. All of you know that solar and wind being infirm power, being intermittent power, and it doesn't follow the demand. Like our demand peaks in the evening while the solar peaks in the daytime. So it will definitely require some sort of grid stabilization measures or battery storage or any other kind of storage. CA has done some modeling in this regard. They have made some energy mix studies, and as per the estimates or result of these modeling studies, we will be requiring approximately 27 gigawatt of storage capacity by 2030 for 4 hours. That is almost 108 gigawatt hours of energy storage capacity by 2030. So the need for battery is there. No disputes or no doubts about that. But how do we set it up? That's the question. So far, whatever we have done is we have done it on pilot basis to establish the technical feasibility. Yes, technical feasibility is one aspect of it, but the commercial side is equally important. If we want to make big investment in the sector, we have to identify the revenue streams it will generate. Because people will make investment in any sector, be it power sector or hydro or thermal or any other commercial sector, when there are identified streams of revenue and there is a certainty of revenue. So far, we do not have any model contracts for procurement of storage capacity. Some possible solution could be the leasing of storage capacity or arbitrage between the peaking power and off-peak power to realize some revenue streams. Or recently, if you follow the Indian power system, you must be aware that last week SECI invited bids for round-the-clock renewable power, 400 megawatts of renewable power, and the tariff discovered was very, very competitive, ₹2.93, which is almost 4 cents, 4 US dollar cents. So there are players who are willing to offer round-the-clock renewable power at 4 cents a unit in India. And obviously this must have been backed up by some sort of storage capacity. So my dilemma is it's not only applicable to battery storage, but for any kind of storage system, that what kind of market framework we should have so that we can have investment in this sector. It is necessary to have an appropriate market framework or regulatory framework to give certainty of revenues to the investors to come up with mega size storage capacity. So the pilot size will happen. And so no doubt that battery cost is going down across the world. It has already come down from $1,000 kilowatt hour to $200 kilowatt hour in a span of 7-8 years. But we need to have appropriate regulation and market framework also. So I want to know what the other countries are doing in this respect. What is the market framework do they have? What is the regulatory model they have to integrate the battery storage or any other kind of storage to stabilize the renewables? So these are the doubts or questions in my mind. And I'm very keen to participate and listen to the presentations made by the participants in this. I wish all the best, and I really look forward to very, very keen and intelligent discussions in this webinar. Thank you so much, Monali.
Thank you so much, sir. And yes, we hope that our experts, both Sudipta as well as Shweta as well as Shubhranshu, will be able to address some of the issues which you highlighted. And I will now, hand over to Shubhranshu to set the context and then take the discussion forward. So over to you, Shubhranshu.
Thank you so much, Manali, Michael, and Mr. Kumar. Thank you again for joining us. And also for setting the marker of what you expect from the following 1 hour. We'll try and address some of those issues. Of course, these are all issues that most jurisdictions around the world are grappling with, but we'll try and address some of those from an international perspective, and also from what we've discovered in the 2 pilots that we have run for PGCIL as well as BRPL. So I'll start sharing my screen and start with the presentation straight away. Just give me 1 second. Am I visible? Is my screen visible?
Yes, yes, it is.
All right, okay. So what I intend to do is, there are 3 parts to this presentation, but before I launch into this, I'll be presenting on the pilots that we've done under the RISE project. And they are primarily 2 different pilots that we've run, one for the transmission at the transmission voltage level, and the other at the distribution level. And I'll touch around, what have been the outcomes so far on these pilots. And certainly address some of the commercial and regulatory aspects that Mr. Kumar pointed out. And then I'll call upon Dr. Lairi and Shweta, our colleagues on the RISE project who come from DNV. They're the Senior Grid Integration Advisors, to cover the international aspects and address similar studies and similar aspects that's been attempted globally. So now, what are the value levers for battery energy storage system in power? So there could be several levers, of course, given that battery can act both as a load as well as a generator in various forms and time frames. It has several use cases. It's a very powerful, part of the grid when it starts to participate. Of course, the call-out factor is ancillary, which has been a fairly successful, part of deployment in the Western grids in particular. Ancillary services have been provided with battery energy storage systems, so primarily around frequency regulation, but around other ancillary services also. And then, of course, at the transmission level, and mind you, the difference between transmission distribution that I'm drawing here is only from a voltage perspective. Clearly, some of the use cases would overlap. From a transmission perspective, it could be upgrade deferral. It could be obviously technical loss reduction when it gets deployed, but a very important aspect is there could be right-of-way conservation. When you actually have constraints around right-of-way, given that this is a non-wired alternative, battery energy storage, it can be powerful in solving some of those constraints, and very important for a country like India where we do have right-of-way constraints in certain segments. Coming to distribution, where, because of the fact that distribution is where the bulk of the revenue is getting generated for the, or all of the revenue is getting generated for the value chain, there are obviously quite a few use cases that comes into play. So I'll call out the first one, which is around ramping. We call it ramping here, and it can put some of the Western audience into a bit of a doubt. But the reason we are calling it ramping is because distribution companies in India primarily self-schedule their own portfolio of generation. We don't go through a market yet, although that energy transition is happening on the ground, and we will have a fairly high level of centralization as far as the market operations is concerned going forward. CERC has laid out a pathway towards that. But as it stands today, a lot of self-scheduling of generation happens. And within that portfolio, therefore, they have to manage ramping. They have to manage the set of generators that they have and manage their constraints. So that is from the perspective of, from that perspective, that storage can be a powerful tool. I will run you through some of the use cases on the pilot that we have tested on this particular angle. Similar to transmission, there can be distribution upgrade deferral, capex deferral. There is, of course, reliability enhancement that's possible under storage deployment. All the energy transition elements, new energy transition elements, whether it is distributed storage or EV integration, can obviously be better managed if we have storage also interacting in some form. And then, of course, arbitrage and peak shaving, which Mr. Kumar also alluded to. And then there is the very important element of avoiding renewable curtailment, both in terms of the current system, which is how do you really avoid curtailment in a system which is currently operational, and then going forward in terms of planning itself. So if you're adding more and more renewables, how do you make sure that the renewable overgeneration during particularly the daytime, when given India's context, how do you really spread it out across other time frames? So that's in the long range, but in the short range, what happens when you run out of flexibility from other sources, other parts of the grid? You would obviously need batteries to fulfill in that flexibility. So these are some of the value levers that we tested on our two pilots. So the first one is at the transmission level. I'll talk through that very quickly. The transmission pilot is a partnership with Power Grid Corporation of India, and I believe Mr. Tiwari is also on the, is on. He can also contribute if he wants. So basically, this was a system which was 1.25 megawatts, planned to be 1.25 megawatts of deployment in 3 different technologies: advanced lead acid, lithium ion, and flow. Flow is running a little delayed, but the other 2 are actually operational. And what our help was provided for was to actually enable a range of use cases. So from dynamic frequency regulation to reactive power support, load following, peak shaving. So all of these 7 or 8 use cases we kind of enabled on the existing system by revamping the controls of the battery system there. And we are going to commission this fairly soon. It's still delayed a bit because of the situation that we are in, and a lot of deliveries of this was actually coming from China. One of the components, I should say, was coming from China, so it's got a little interrupted, but we are ready for testing this on the ground. But there are two additional, additional benefits, co-benefits, which are emerging from this pilot. That one, we will be able to finalize standards for BESS interconnection onto the grid. And the site acceptance testing, which is so important for battery energy storage at scale, will also get standardized under this pilot. So for larger pilot deployments, larger battery deployments in the future, you will have site acceptance standards fairly well established under this pilot itself. Now there is another component of the transmission level battery energy storage system which we modeled. This is for the southern grid, and this was essentially a simulation study that we carried out, which was along with PRDC. PRDC is our partner on this, on the simulation studies. So what we essentially wanted to find out is what is the contribution of battery from the perspective of frequency management. So both primary as well as secondary frequency management. So from that perspective, how is battery going to play a role and in a real-time environment? So what we did was to model the system, simulate the southern grid in its entirety, and looked at primary and secondary frequency contribution of batteries of various capacities. And what we found was that about 1,200 megawatts of battery would effectively replace the 3,000 megawatts of spinning reserves that we currently require. And we hold this out, by the way, in the Indian system. Those who are familiar with it, with IEGC, we actually don't allow for our generators, primarily the conventional generators, thermal generators, and also storage hydro, to go beyond the installed capacity in terms of scheduling. While they're capable of going to 105, 110% of the installed capacity, we hold this capacity at installed capacity level itself, because the balance is something that we require for primary as a primary reserve. So that is specified, that's specified under IGC, and therefore held back. And if you were to say that that is about 3,000 megawatts in the southern grid, which came out of the modeling, by the way, it's not something that we're defining here, then a 1,200 megawatt battery system could effectively replace the need for holding 3,000 megawatts in reserve, in spinning reserve. And effectively, that would mean that this 3,000 megawatts can participate back in the marketplace. And that would effectively bring down the pricing of energy by almost 10 paisa overall in the southern grid. That is a significant benefit. If you were to see, then that benefit essentially translates to 3 times the cost of the battery itself. So this is something which we kind of now presenting to CERC and also to the other stakeholders. And at some point, this needs to be looked into, that battery can actually provide a significant amount of primary and overlapping secondary frequency regulation, and can release the locked out reserves that we are holding from the conventional generators in general. The second pilot is around distribution, and basically what we did was to analyze the business case for a 20 megawatt BESS to be deployed for a private distribution utility in Delhi. And there are 2 components to this. So one component is, of course, to build the business case itself, to build the commercial business case around whether it makes sense to at all deploy this 20 megawatt. 20 megawatt came as a given to us, of course, but we ran simulations around what is the quantum that can be taken by the system and such. And the second part is actually creating also a regulatory business case, because again, in Indian context, distribution is a completely regulated business. And therefore, one has to get regulatory approvals for investing in the CapEx or going into a contracting mechanism that Mr. Kumar was also alluding to. So for both components, we assisted BRPL in this case on the ground. And the actual interventions were in designing a a model for value estimation, which is a combination of a network model and a value optimization model, which is both analyzing longitudinally what will be the benefit over the time, over the life of the battery, as well as looking at what the opportunity is of operating the battery in different time scales. So it is a dispatch simulation and also doing it longitudinally over time. I'll not spend a lot of time around how we went about, what the mechanics are, but there are three aspects which are coming out as extremely valuable in terms of the modeling outputs. One is, which I term as ramping, but you can use any term. Essentially, if the distribution utility has to manage the portfolio of its generation, there are two options that's emerging. So if for instance, the evening peak has to be managed, it has to either let go of some of the solar, or it has to essentially, operate suboptimally some of the generation because of the ramp constraints that conventional generators have. Now, all of this could be removed if you have a battery in the system, clearly, and you could very seamlessly operate in a smoother fashion all your generation. So that's the crux of the use case that we tested. You could also term it as curtailment of renewables avoided. That's also one of the ways of looking at the first bullet. The second aspect is, of course, energy arbitrage, which is pretty well understood, so I won't spend a lot of time. Clearly, in the peak, there is a lot of consumption that happens in Delhi, particularly in summer months. It's a fairly peaky load. How do you avoid tapping into fairly high cost marginal stations? That's something that BESS can enable. And the third element is, of course, capacity deferral, particularly if, in terms of locating the battery systems. Can we locate it where the system is already overloaded, and we can buy some time in not investing in the capex in certain substations by deploying the battery there. So those are the three specific use cases that got enabled. This slide also talks about primarily those three use cases. And what I'll leave you with is, these are some of the outputs that's come out of the study. So if you look at 2021-22 timeframe, then the ramping support is required possibly over just about 4 months in a year, 3 to 4 months in a year. But if you were to look forward to 2027-28, then that's required almost over 6 months in a year. And the surplus that's available for battery charging is almost completely round the year. You get that surplus in 27-28. You get it possibly over half the year in 21-22. So these are some of the insights. But if you were to put a battery today in the 2021-22 time scales, what's come out as instructive is that the battery would still be valuable, but it is possibly giving value which is about 30% less than the cost. So the cost outweighs the battery value at this point in time. But and there are two caveats to that. One, that we are taking OEM given costs. So if you were to hold a competitive process, maybe the cost will come out to be lower, and there are sections of the industry which believe that the cost should at least be 20-25% lower. So we will not comment on that, but that's definitely one of the possibilities. The other is that there is a sustained reduction of almost 8 to 9% year-on-year in battery costs. So if it's not 2021-22, then certainly it can become viable in a couple of years' time. So that's what I'll leave you with. This is exactly what's coming out of the pilot outcomes. I'll pause here. I'll hand over to Dr. Lahiri, and then we'll come back for questions at the end. So Sudipta, over to you, Shweta and Sudipta, to take us through the international experiences.
Thank you, Shubhranshu. Let me first try to share my screen. Ripu, let me know when you can see my screen.
You should be able to now. You can see it, yeah.
Okay. Thank you, Shubhranshu. Hello, everyone. First of all, I hope everyone is staying safe and staying healthy wherever in the world you're joining from. At last count, we had registrants from over 96 countries. So I welcome all my colleagues from all over the world. I'm excited to be with you today, speaking about something that has been the focus of my work and is very close to my heart: energy storage projects and how to deploy them profitably and safely. The time we spend here is entirely for you, so definitely post your questions in the chat window. We already received a bunch of questions over the past couple of days. We'll get to as many as we can. We can also stay in touch and continue this conversation after the webinar. I'm based in Philadelphia on the East Coast of the US. I've been in the energy storage industry for 12 years, so since its very inception, and with DNVGL for 9 to 10 years. Just to put our information in context, I'll present a little background about where we are coming from. DNVGL is the world's largest independent advisory firm in renewable energy and energy storage. And we have been engaged in over 2,000 megawatts of energy storage projects in North America. Our services include modeling and valuation, owner's engineering, independent engineering, and testing. And then most importantly, the stuff we'll talk about is not an abstraction. It's from our on-the-ground experience. We have a packed agenda for you. This talk has 4 sections. Section 1 talks about the components and subcomponents of energy storage systems and how they're packaged together. Section 2 looks at the most popular grid storage applications currently in North America, current contracting and commercial trends. Section 3 goes in detail on storage costs. We present a case study. We present merchant market benefits and revenue streams and show a case study of storage dispatch. And then section 4 is probably the most important. I wouldn't say probably, is the most important. Requirements for storage safety. So without any more delay, let me hand it over to the real expert, my colleague, Shweta Sundaram.
Thank you, Sudipta, for that introduction. And hello, everyone. Thank you very much for joining us today. I'm Shweta Sundaram. I'm a senior consultant with DNVGL. I've been in the energy storage industry for the past 4 years, and glad to be talking to you all through this webinar today. So before jumping into the details of battery system specifics, I just wanted to set the stage with this slide on global storage market projections. As you can see on the chart at the bottom, this is a very optimistic picture for the global storage industry. We are expecting to have almost 1,000 gigawatts of storage by 2040. In terms of countries leading, the US and China are expected to lead the lion's share of deployments, but India also has a sizable piece of the pie. In terms of there are several positive drivers that are going to make this a reality. Perhaps the most important is the global movement towards renewables adoption and increasing motivation to move away from fossil fuel generation as we are more aware of climate change impacts. And this bodes well for the storage industry as well. Next, the costs. Sudipta, if you could go back. Yeah, thanks. The costs and performance of renewables as a whole, as well as storage, has improved quite a bit over the past decade, giving the technologies much needed comfort and confidence. And finally, there's been tremendous financial backing for storage companies, especially in the Western countries. Of particular note is the fact that a lot of European energy giants like Enel, EDF, and Total have invested in renewables as well as storage development companies, providing much needed financial backing for projects. However, there are several challenges that need to be overcome before this projection can be a reality. As has been already mentioned, there needs to be an upgrade to regulatory and market design in almost all parts of the world to compensate resources like storage effectively. And There's perception of high prices of the technology. It's still viewed as a novel technology, and the market is still not mature, so there's a lack of standardization of products and projects. So this leads to the cost still being perceived as high, but we're seeing that trend change rapidly as the market matures in the West. Next slide, please. So jumping into some battery system component basics. So for the purpose of this webinar, we'll be focusing on lithium-ion batteries as the technology, as we're expecting that to be the dominant technology for the near future at least, and focus on utility scale systems alone. So this picture here is a containerized solution that you would see at any typical utility scale storage system. At the very granular level, there are the battery cells, which are, of course, the building blocks, which are packed into modules and racks that you see in the schematic here. And this is housed in an enclosure or container. There's also the battery management system, which is an important piece of control software. That monitors several parameters of the system, such as cell voltage, current, and temperature, and also does cell balancing to optimize the system's performance as a whole. Also, an important piece layer here is the thermal management system. That's both at a module as well as enclosure level. So this provides much needed temperature balancing for the cells as the cells get heated as they're used, and this is degrading to their performance. So this is in the form of air-cooled HVAC systems or liquid-cooled systems, and we'll see shortly why that's a critical piece of the design. Moving on to the next slide. Looking at slightly the bigger picture, so the schematic on the right here is a representation of a very high-level storage system at a project level. The inner box here represents the container that we were just looking at. Typically, there are several containers depending on the size of the storage system. These are then connected to power electronics equipment like inverters, much like PV system inverters, transformers, switchgear, and other auxiliary electrical equipment to connect to the substation itself. Then there's the energy management system, which is the controls gateway between the scheduling coordinator or dispatch operator and the site. And as storage systems are getting more mature and sophisticated in their applications and dispatching strategies, EMS offerings by vendors are also getting sophisticated to be able to relay these dispatch strategies and optimize the system's performance. Finally, there's the fire protection system, which is a hot topic, as Sudipta was alluding to, given some safety concerns around lithium-ion as a technology. He will be going into the details of that at the very end, so we'll skip over that for now. Moving forward, in terms of design considerations, perhaps the most unique element of storage system design is the degradation. So this is not really a new term to us. We all use cell phones and we see that battery lives go down as we use the phones. So stationary systems are no different. Batteries lose energy, capacity, and efficiency with use and over time. This is a pretty complex phenomenon, and there are several known drivers of degradation, which are listed here on the left. So there's the total energy throughput, or how the system is being used. The average state of charge, which higher that is, the worse it is for degradation. The depth of discharge, so going from 0% charge to 100% back to 0% is worse than, say, going from 20% to 50% to 20%. Then there's the C rate, which is the ratio of power capacity to energy capacity, an important metric for utility scale systems. Higher that is, the worse it is for degradation. And then there's temperature, operating temperature, like we just saw. So as you can see on the chart on the right, it's an illustration of the impact of temperature. So the cells show better capacity retention when they are operated at 25 degrees C, shown by the dotted lines on top, compared to 10 degrees C. So outside of the 20 to 30 degrees Celsius range, the cell's performance drops quite a bit because there's a lot of degradation. Just a small note here, this data was obtained by cell testing in DNVGL's laboratories, and we've also modeled the degradation using our proprietary tool called Battery XT, which combines real-world cell testing data with theoretical degradation models. So if you would like to use this service offered by us, please get in touch after the webinar. Moving forward with the design considerations. So in terms of designing utility scale systems for a contract, typically the developer is held to a capacity guarantee that they need to maintain for the whole contract term. And they need to account for degradation while sizing the system. So they do this using one of three strategies. First is oversizing, which is shown by the chart on the blue line on the chart. So in this case, the developer installs more than needed capacity at year 0 and lets the system degrade so that at any given point in the contract term, the capacity is at least as much or higher than the guaranteed capacity requirement, which is the dotted line there. This may be cost effective for smaller systems like less than 10 or 20 megawatt hours because you don't have to re-incur installation costs. But what we're seeing more commonly is a replacement or augmentation strategy where the developer will replace degraded racks or add in new racks to give the system a boost of capacity at fixed points in the future. So this is often more cost effective for larger systems because we can make use of projected battery cost declines and bring down the whole system's cost at year 0. Having said that, the degradation is also heavily impacted by operations. So how many cycles or the annual throughput of the system, the C rate at which it's operated, and so on. So these are also important considerations that need to be accounted for in the design. Now, moving to the next section, we'll talk about grid scale applications and then touch on commercial considerations. So in terms of applications, Shubhranshu was just talking about this a few minutes ago. So as we all know, storage is highly flexible in the fact that it can be used to serve a wide range of applications depending on the point of interconnection. It's also flexible in terms of sizing. It can have different durations or megawatt hours depending on what's optimal for that application. So some of the more successful applications, like it was alluded to, is for storage to provide ancillary services, especially frequency regulation. This is because of how fast responding these systems are. And you need typically a short duration system to provide such a service. On the longer duration end, more than 1 or 2 hours is what we're seeing now. Storage is used to provide capacity and also be co-located with renewables, especially solar, because of the host of benefits it brings from being able to shift energy, capture energy which would be otherwise wasted, or smooth the output of an otherwise intermittent system. At the transmission and distribution level, storage can be used to solve specific network issues, like provide voltage support, reactive power support, and so on, and also help distribution operators defer expensive upgrades, which is an indirect cost saving that can be passed on to the developer. And these may be very specifically useful for the Indian grid context, given that storage may be effective for solving network issues in highly congested areas as well as rural areas, wherein other network upgrades may be expensive, because storage occupies such a short footprint and it's also fast to be installed. So which are the applications that are actually cost effective? On the next slide, we see the installations of storage in the US historically as per application. So as is expected, frequency regulation and capacity-based requirements have been the dominant application, as well as T&D deferral projects. But what we're seeing is co-location with renewables, especially solar plus storage, is going to be the dominant application for storage attractiveness at scale. So this is gaining rapid momentum right now. Most of these projects rely on bilateral contracts, so they have a fixed revenue stream with an off-taker. But what we call merchant projects, which is, at least in the US, the resources are able to participate in wholesale energy markets administered by independent system operators and make revenues there. These are also gaining investor confidence. Having said that, the economics are highly dependent on the location or market as well as policy conditions. In terms of markets, for instance, the US Northeastern market called PJM was extremely lucrative for storage to offer frequency regulation because there was a premium for the compensation, which led to flooding the market with energy storage. And similarly, in states like California, where there's a lot of solar penetration already, there's a sizable arbitrage opportunity between on and off peak energy prices, which creates the natural business case for storage. Perhaps more importantly, there's policy and regulatory drivers at both the federal and state level in the US, which we'll see on the next slide, which have really spurred the adoption of storage. So at the federal level, the Federal Energy Regulatory Commission, or FERC as it's known in the US, has issued orders that instruct the independent system operators to create fair market rules for storage to be able to participate and get compensated in the wholesale markets, and for compensation to be commensurate with the flexibility that storage systems provide to the grid. Next, there's the solar plus storage investment tax credit, which has essentially spurred that industry, and it's really created the business case for that industry as a whole. Then there are several state level mandates and incentives. For instance, California is one of the pioneering states issuing these kind of initiatives for power companies to adopt storage for capacity requirements. In the US Northeast, in New York, we have seen initiatives for power companies to specifically look at storage for T&D deferral projects. And these companies are often able to rate base storage and make a return on them when they are proved to be cost effective. And finally, power companies are also considering storage in their traditional independent resource planning processes. So all of these have been a tremendous sign of confidence for the storage industry and spurred the adoption. On the next slide, we'll talk about cost effectiveness, and value stacking is a very critical piece of that for storage. So again, as we know, storage is flexible and it's unique in that it can be used for more than one application or use case at the same time. So this leads to stacking of applications or stacking of revenues, which has been critical for storage to be cost effective so far, and we expect that to continue at least in the near future. So for instance, a single storage system can be used to provide both capacity to an off-taker and also participate in the market and make money from, say, energy arbitrage. And Sudipta will go into a lot more details of this in terms of stacking and how to actually model the performance and revenues from stacking. So I'll move on to the next slide, which is a note on solar plus storage, because we think that's the next big thing for energy storage. So most utility scale solar projects in the US are expected to be paired with storage going forward, recognizing that storage enhances the economics of the system as a whole, like we mentioned, by doing energy shifting, by reducing curtailment, and by smoothing outputs and so on. We're also seeing innovation in the design of solar plus storage projects from being AC coupled to DC coupled. In the latter, that's especially beneficial to capture otherwise wasted energy. And We're seeing that PPA prices for solar plus storage have fallen tremendously, as shown on the chart, the bar chart. So now they're hovering at about $30 per US dollars per megawatt hour, and they're often competitive with conventional generation resources. Power companies are also comfortable with thinking of them as alternatives to conventional resources. And storage sizes are only getting larger as costs decline and the realized value from the whole system increases. Next, I'll touch on commercial considerations very briefly in the interest of time. So these are some contract structures which we're seeing for energy storage at utility scale. So there's the tolling agreement, which typically involves a fixed capacity payment at $1 per kilowatt month rate that the off-taker pays. The developer is responsible for developing, owning, and operating the asset, but the off-taker typically keeps the revenues generated by the storage system. Then there's the capacity agreement, which is very similar, but that the difference being that the developer typically keeps the revenues and often prices that into the dollar per kilowatt month value so that it's more competitive for the off-taker. Then there's turnkey projects where typically large companies like power companies or discoms can buy storage asset as a whole and use it at their discretion. And finally, there's renewables plus storage, which is a bundled dollar per megawatt hour PPA. And sometimes we see a premium being offered for production at certain peak hours, which makes it a beneficial use case for storage. Lastly, just briefly touching on considerations for contracting from an off-taker point of view. The off-taker should definitely account for or make sure the design accounts for degradation for the use case or use cases being considered for the project, and also that it covers performance guarantees that the developer would offer. So the operator of the storage system typically applies constraints on operations like limiting the annual throughput, limiting the C rate, and so on. And these become equally important considerations while contracting other than just the pricing itself. With that, I'll turn it back to Sudipta to walk us through storage cost components.
Thank you, Shweta. Before I start, let me just recap or tell you in advance what I'm going to talk about. The first 5 minutes of my talk is going to cover storage costs, the cost side of the ledger. The next 5 minutes is going to cover details and case studies of the benefit side of the ledger. And then the final 5 minutes will be on safety and compliance. So in all, I'm expecting 15 to 17 minutes, and we should be wrapped up at 10:45 and ready for your questions. The storage cost. Generally, in most of my talks, the section that gets the most excitement is storage cost trends. Follow the cursor here. This is where I started my career in D&D. At that point, around 2010, 2011, we were seeing storage costs in the range of $3,000 to $5,000 per kilowatt hour. And this is where we are now in 2020, in the range of $300 to $400 or even lower per kilowatt hour. In fact, in one of my first projects, where we worked on cost effectiveness methodologies in support of California's AB 2514 mandate, we were looking at costs between $3,500 to $4,500 per kilowatt hour. That has come down 10 to 12x. All the numbers I'm presenting here are generic median numbers based on our experience and available in public information. And these are not related to one specific project. However, in 2016, the cheapest project that was deployed, the most cost-effective project that was deployed was in Southern California. The Aliso Canyon project came in at an all-in cost of $550 per kilowatt hour. In 2018, we were seeing examples of 4-hour projects at $400 per kilowatt hour. In 2019, 2020, we have been seeing projects that are going to be deployed or scheduled for 2021 plus deployment. 4-hour projects in the range of $275 to per kilowatt hour. You can see the rapid declines. Now, when we talk about storage costs, it's very important to understand the baseline, what we are talking about. Storage project costs, all-in project costs, accrue to goods and services provided by mainly three parties. The first case is the battery manufacturer or the storage technology manufacturer that provides the DC side of the system, cells, modules, and the battery management system, the BMS. The system integrator takes the system, packages it into a battery energy storage system, along with grid controls, inverter, and in a containerized solution that has monitoring, HVAC, and safety mechanisms. And then finally, the project developer invests in the site, develops the project, and there are additional costs on site preparation, electrical balance of system, construction, and commissioning. At each stage, the party has a cost multiplier given by 1.1 to 1.5 in the system integrator case, and 1.2 to 1.8 in the project developer case. So for DC side systems in the range of $150 to $300 per kilowatt hours, the cost builds up to between $300 to $1,000 per kilowatt hours in some extreme cases for the all-in project. Now, what we're presenting here is an example of some ranges of all-in project costs. And what we have done here is broken down the project cost, the capital and operating project cost, into the most logical subcomponents. Note that the cost ranges are intentionally kept broad to accommodate differences between technologies and solutions. First, you have the DC side modules and BMS between $200 and $500 per kilowatt hour. Power conversion system or inverters between $70 and $110 per kilowatt. Grid management control system, this is separate from the BMS. These are the grid controls, between $20 and $50 per kilowatt. Electrical balance of plant, installation and commissioning, between $80 and $200 per kilowatt. Services, tariffs, and contingency, between $50 and $100 per kilowatt hour. In terms of O&M costs, preventative maintenance costs may be attributed at $3 to $7 per kilowatt year, going through the life of the project. Capacity maintenance cost, this may be based on the amortized capacity replacement cost at $100 to $250 over the lifetime of the project based on installed capacity. On an annual basis, this may be anywhere between $5 to $10 per year per kilowatt hour. And then equipment insurance fee between 0.5% to 1% of CAPEX per year. So now we work a case study or an example of a typical project cost. Assume that this project is 20 megawatts and 80 megawatt hours. Note that some of these costs are applicable to the energy capacity in dollars per kilowatt hour, and some of these costs are applicable to the power capacity, or at least that's the way we split it out so that it adds up properly. The power capacity costs are attributed in dollars per kilowatt. So these are some example numbers that we have taken. For this 20 megawatt, 80 megawatt hour project, the total costs may add up to around $29.6 million. That's an average of $370 a kilowatt hour for this example project. Note that this is a 4-hour duration system. If you were to build, or if you were to do the same example for a 2-hour duration system, it would have 40 megawatts of power capacity, 80 megawatt hours of energy capacity. And if you were to apply the same units for the 2-hour energy system, the total cost would have been $35.2 million. So that works to around $440 per kilowatt hour. Generally, what we are seeing is that the DC side technology cost is between 60 to 65% of the project cost. The PCS, the inverter and controls, is approximately 10%. And then balance of plant and project development costs are 20 to 30%. Note that there is quite a bit of variability and uncertainty in these costs, and they depend quite a bit on where the project is being installed, the permitting, the local permitting and regulatory requirements, the site control requirements, whether the project is being installed in an urban area, in a suburban area, or a rural area. So what I spoke about was the past and the present. This is what we are expecting for the future. These are, again, typical project costs that we are seeing today for different chemistries of battery systems. These include lithium-based chemistries, such as LTO, lithium titanate, as well as NCM and LFP, which are the most popular chemistries of the lithium-based batteries. It also includes zinc bromide, zinc air, as well as vanadium redox flow batteries. So generally, for all these chemistries, what we are expecting is a 30 to 40% reduction in cost over the next decade. So by 2029, we're expecting all-in project costs to reduce between 30 and 40%. So for example, the project that was around 30 million in the example that I worked out, maybe around 17 million in 10 years. These cost reductions, the main drivers are increased production capacity, so reduction in the DC side manufacturing cost, increased production capacity and supplier diversity. Again, the first 2 points are related to increase in the DC side manufacturing cost. Incremental performance improvement, so this is how these DC side and package solutions are created. These cost reductions will be attributed to better packaging and better integration of the system. And then finally, some reduction in project development and engineering costs. Note that most of the reduction that we are expecting is in the first 2 points and not in the second 2. Generally, what we are seeing is that the trajectory of storage cost is very similar to historical solar cost trends. And even before that, it's similar to wind cost trends. The storage industry is right now in an early adoption phase with project financing at its very inception. So as the financing community, as more projects are accepted by the financing community for long-term financing, we'll see much higher and much deeper cost reductions. Let's talk about that's all about costs. Now let's look at the other side of the ledger, benefits. So generally, the way that I've organized this section is that storage benefits depend on 3 things. Number 1, regulatory, like Shweta mentioned. Fair access to markets for storage and fair compensation for services. Number 2, tactical. Application bundling in order to take full advantage of storage systems' unique technology characteristics. This is based on the sophistication of storage controls. And based on an operational level. And then number 3, strategic. Essentially strategies to balance income with resource loss from degradation. And this is strategic. This is generally on a medium to longer term outlook. And I'll touch on all 3. This is a map of the North American system. Well, it's hardly a system, but what the colored bits that you see here are North American independent system operators. These are structured markets and balancing areas. PJM is the largest, followed by Midwest ISO, California ISO, ERCOT, New York ISO, SPP, and ISO New England. Together, they serve 65% of US electric customers and has 56% of all installed generation. In 2018, the Federal Energy Regulatory Commission, so the body that regulates interstate energy systems. So ERCOT, which is a Texas market, contains solely within Texas, is not subject to federal or interstate jurisdiction. However, we are talking about FERC Order 841. In 2018, 2019, this order was introduced or passed by FERC. And this order required all 6 US ISOs, all ISOs except ERCOT, to provide equitable or fair access to storage systems to all operating and non-operating markets. And it required storage systems to be considered both as generator and load. This slide covers the list of the different markets and services. When looking at these, you don't need to have your energy market hat on. These are more general. In vertically integrated systems where markets don't exist, storage compensation would still be based on these services. When procuring storage through a bilateral contract, these services are rolled into an overall offtake or a PPA. So the valuation, the benefit of these services are rolled into an overall power purchase agreement. So looking at this from left to right, capacity markets or capacity value is for the capital cost recovery of the asset and is based on the contribution of the asset to support peak demand. It doesn't require the asset to respond to an operating signal. On the performance side, you have energy services, day-ahead energy and real-time energy, hourly or sub-hourly. On the ancillary services side, you have real-time power balancing, which is called frequency regulation in US markets. Again, this is in the Indian context, this is secondary frequency regulation and not primary. You also have spinning reserve and non-spin reserve. So that's point 1, equitable market services. Let's talk about point 2, sophisticated controls and dispatch strategy. So generally, in order for the battery system to bundle and respond to all these different markets, internally the control system has to perform a dispatch optimization. The requirement is to maximize the expected operating income of the storage asset under forecasts of market prices, forecasts of renewable production, ancillary service performance requirements, while maintaining an acceptable state of health and complying with market regulations, interconnection requirements, and any incentive requirements. And generally the day-to-day dispatch or hour-to-hour dispatch is based on all these different criteria. You know, these are the list of markets and services the battery system should perform in. The technical requirements of project hybridization, which renewable asset you're combining the battery with and how you're combining it with, and then other interconnection, tax, and contractual requirements. So let's look at a case study of how this is done at the operational level. What you see is an example dispatch simulation of a DC coupled solar plus storage system. This is picked on an example day on 17th of August, for example. And this is the optimal dispatch strategy in the following markets: energy and regulation. It says day-ahead energy, real-time energy, day-ahead regulation, up and down, and spin reserve. What you see at the top are the prices. What you see at the bottom are capacities of the battery participating in different services, as well as being bundled at the same moment in time. The corresponding operations of the battery is shown in this slide. At the top, you see the output of the PV plant, and the red bits is free charging from the PV plant from clipped energy. At the bottom, you see the battery charging and discharging signals, as well as the state of charge of the battery, tracking this optimal dispatch. Now, the final point, the strategic aspect of income versus degradation. The idea is to have a bidding strategy of the battery so that you are maximizing the income of the battery while minimizing the cost of resource loss from degradation. And generally, as you impose cycling limitations, the system prioritizes cycling only when it is increasingly valuable to do so. In this left graphic, you see the difference between cycling 2 cycles a day versus 0.6 cycles a day. The left axis is the 1-year income. millions of dollars. So in the first case, 2 cycles a day, the income may be around 5.5 million. For half cycle a day, the income is 3.5 million. But the value per cycle is much more. In the first case, it's $7,600. In the next case, it's $15,000. The degradation of the battery is much different. In the case of 2 cycles per day degradation, it's 70% in year 13. And in the case of 0.6 cycle per day operation, it's 70% in year 20. So what we have covered are the 3 aspects of battery benefits: regulatory impetus, tactical operational aspects of bundling sophisticated controls to bundle different applications, and the number 3, strategic aspects to maximize income while minimizing resource loss. So this brings us to the final and the most important element of storage projects: storage safety. So before we get into these slides, let me just make a quick disclaimer. Some vendors and manufacturers may claim that their chemistry or technology is safer than others. Generally, DNVGL does not support these claims at a broad level. Integrated systems and projects should follow latest standards and guidelines in storage safety, and a lot of this is determined by testing and modeling. So the topic of storage safety has got a lot of attention over the past 2 years, particularly after a high-profile incident in the US and several incidents in South Korea. Just a little bit of information on where this is coming from. The NVGL has been involved in storage safety for around 8 years. We do battery burn testing in our labs in Rochester, New York, and in Columbus, Ohio. We do firefighter training. We have been working with New York State and Fire Department of New York in coming up with standards and best practices of battery fire safety. A lot of attention in the past year is coming up with appropriate standards for storage system design and system permitting. So this slide shows the main codes and standards required to be followed by each subcomponent of the energy system. For battery cells, modules, and racks, you have UL standards 1642 and UL 1973 for safety. For battery container, you have NFPA 70. For the integrated battery system, you have UL 9540 and NFPA 855. And you'll hear a lot about these two, UL 9540 and NFPA 855. These are the latest safety standards. NFPA being National Fire Protection Agency. And then for AC and DC, for the power conditioning system and electrical requirements, you have UL 1741 and IEEE 1547, as well as any standards based on local jurisdictions like California's Rule 21 for inverters. So thermal runaway, let's understand a little bit what the primary hazard in batteries are. To do that, we have to understand the concept of thermal runaway. This is a situation when heat generation within a cell is self-perpetuating. So it feeds itself. And this is caused by electrochemical processes in the cell. Because it is self-perpetuating, it will not be removed if the abuse condition is removed. The thermal runaway is caused by prolonged or severe exposure to abuse conditions. These abuse conditions may be thermal, for example, high temperatures in excess of 250 Fahrenheit, which is 120 degrees Celsius. Electrical shorts and failures are mechanical. Crushing, pressure, shooting, a truck driving into the battery, someone shooting at the battery, etc. Under an abuse condition, a battery system will generally emit off gases, and these can be detected for mitigation. Preventative actions can be taken to remove the abuse condition from the battery before the battery goes into thermal runaway. For example, one of this is venting. You know, the tops of most lithium cells pop off, or pressure release and venting, and this removes the abuse condition. Another example of preventative measure is tripping off electrical components. Essentially, if the abuse condition is removed in this region, then the battery, you can stop the battery from going into thermal runaway. Once thermal runaway starts though, design standards require that several suppression and containment procedures be designed and initiated. It also requires that the abuse is not propagated. Now, what are these design standards? The number one is cascading layers of protection, or concentric layers of protection. Energy storage systems are recommended to follow safety by design philosophy. They are required to have concentric layers of protection. For my Hindi-speaking colleagues, safety measures are required to be like Mahabharat's Chakravyu. At the outermost layer, you have monitoring for off-gases, abnormal thermal or electric conditions. At the next layer, you have preventative measures like venting, HVAC, mechanical disconnects, and electrical disconnects. At the innermost layer, you have suppression and containment strategies. Like we are following social distancing these days, the system subcomponents are required to have clearances and safeguards, such that their thermal runaway in one cell or rack or module is not propagated to the next, not propagated to the others. This requirement is actually ingrained in NFPA 9540. The testing requirements for that are in 9548. In the worst case scenario, if the Chakravyu is breached, training and procedures should be in place for emergency responders. Just from our experience, in the event of a container fire, the recommended strategy is to let the fire burn out and contain the fire through water sprays from a safe standoff distance. Do not open or enter the container without prior approval of the project safety expert. Again, this slide has some fire and safety takeaways obtained from our experience of burn testing and suppressing battery fires. I won't go into this slide in detail, but the general idea is follow the safety by design philosophy, and all these requirements are encoded in the latest safety and thermal management standards. These are the list of standards that everyone, all battery system professionals and battery project engineers should keep in mind. NFPA 855 and IFC, International Fire Code 2018, and the latest 2021. UL standards, UL 1642 for cell, UL 1973 for module, UL 1741 for inverter, UL 9540 for system, and then 9548 is the recommended testing method for battery systems. Final takeaways: regulatory changes are required for providing fair access to energy storage systems, harnessing its technology benefits, and providing fair compensation. One example is that the US market was spurred by FERC Order 755 that was issued in 2011, FERC Order 851 issued 2018-2019, and California State Mandate AB 2514 that required the IOUs to deploy cost-effective energy storage projects. Project economics depend on three things. Number one, rapid cost decline. Number two, fair access and compensation mechanisms. And number three, sophisticated controls for bundling services and realizing benefits. Renewable plus storage projects has strong financial points due to the appeal of free energy from clipping or curtailment, as well as tax incentives, particularly in the US. Storage operating strategies have to balance between maximizing income and minimizing loss of the resource. And this is at a medium to long term. New standards for storage safety must always be followed, and safety by design should be a guiding philosophy. So thank you, everyone. Thanks for your attention. Let's open the floor up for questions.
Thank you. Thanks, Adipta. Thanks, Shweta. That was pretty insightful. I have a list of questions which has come through. So let me start by picking up Mr. Kumar's question. In fact, he sent in a question asking, what what regulations could be of value to promote, energy storage systems in India. So what kind of regulations would possibly be required? Shweta, would you want to take that?
Sure. Yeah, Shubhranshu, I can take that. So the answer is that it's going to be a mix of different kinds of regulatory pushes. That's what we've seen in the US. First of all, there needs to be a central vote of confidence for storage projects from the central government level, much like there's been from the federal level here. And there need to be compensation mechanisms that are enabled that compensate storage appropriately and competitively with other resources. And a few more examples is making sure you enable multiple value streams for storage. That's one topic that even in the West, it's still being discussed as to how exactly to make that happen operationally. But as we discussed, that kind of value stacking becomes critical for cost effectiveness of storage. And other innovative examples are we're seeing with like solar plus storage PPA structures. Sometimes there's a premium offered in certain on-peak hours in the evening. So this incentivizes the adoption of storage with solar and enhances the business case for the whole system. So considering that India's gotten a lot of interest in renewables, especially solar, this may be something to think about. But yeah, it's going to be a mix of central as well as state level initiatives to push storage adoption from a regulatory standpoint.
Thank you, Shweta. Thanks.
Let me pick up another question. This is coming from Mr. Dharmendra Umaramani from Shell Energy, London. Who are the main international manufacturers of battery cells by chemistry? Sudipta, would you want to take that on?
Quick request, Sudipta, can you stop sharing your screen? Maybe we'll put the panel on. Yeah, thank you.
Generally, in lithium chemistries, there are a few Korean, the main manufacturers are Korean and Japanese, as well as some US manufacturers. These are for NMC chemistries. For LFP chemistries, the main manufacturers are in China. And then system integrators are generally European, American, or Chinese.
Right. Maybe we can ask Mr. Manish Tiwari is also on call. He's a senior, the chief general manager, I should say, at PowerGrid, and the architect of the PowerGrid pilot project. Mr. Tiwari, who all have you encountered from which countries for the various chemistries? Because you tested out all three. Maybe you can throw some insights on which country manufacturers you encountered.
Mainly from China for LFP batteries. Actually, ours was LFP, but definitely there are Koreans and Japanese. Some US manufacturers are also there. For flow batteries, we explored market where US is there, in Europe also, Germany. There are flow battery manufacturers. In China also they are there. There are some companies which are US or Canadian based, but they are having manufacturing capacity in China. Main manufacturing is taking place in China, Germany, Korea, Japan, and US.
All right, thank you. Thanks, Mr. Tiwari.
And one more point to keep in mind is the value of the entire integrated system. So the cells are only a component, sometimes even a less than 50% component in terms of the integrated system's value. So the cell manufacturers may be concentrated in East Asia and Germany, but then the integrated system may be manufactured or assembled in different places in the world and closer to the sites.
Right. Another question coming in from Erdal Sahin from Turkey. He works in GTG-RISE. Can you provide an example of a case study of energy storage system with a payback period? What was the estimate of a payback period there?
So payback periods we are seeing, particularly with the investment tax credit incentives for solar plus storage systems. For storage systems, we are seeing payback periods that are in the around the 5-year range. Sometimes it's less than 5 years, sometimes it's a little more than 5 years. The interesting thing is that project financing of large-scale utility-scale storage projects is in full swing for fixed revenue or fixed contracted projects for the ones that are procured through bilateral contracts such as PPAs. Increasingly, the newer projects that are being deployed have a somewhat hybrid strategy where they have a fixed contract for parts of their services, and the remaining part of their services is free floating for merchant revenue. So I think the frontier of financing of storage projects will be project financing of merchant revenue projects.
Right, thank you. Thanks, Dr. Lahiri. So there are some questions on my presentation, primarily around right of way that I mentioned and how that could possibly work. So let me just clarify that because there are multiple questions on that. So the way it works or the way it's conceptualized is pretty similar to high-powered conductors. And if you have, storage enabled, you are basically enabling higher transfer of electricity on the same infrastructure. So it effectively avoids right-of-way considerations or right-of-way for a new line. So it's primarily an augmentation of an existing infrastructure. So it's very similar to the HPC considerations that you'd evaluate. This is a non-wired alternative to that. So that's in the nature of how I mentioned ROW in that particular presentation. So, right, so I think we're dot on time. We've come to 8:30. Is Tushar on, Ripu?
Tushar is on, yeah.
Okay, can we request Tushar for a vote of thanks and closure? I think we've come to 8:30 and I'm conscious of time considerations for everyone. So Tushar, if you're on.
He's unable to unmute himself. I think you can go ahead.
All right. So
we do have a quick poll though.
Yeah, sure. Yeah. So we do have a quick poll. How do you go about it, Ripu?
I have kind of launching it at the moment.
Okay, so we can request participants to vote on it, on how their experience was. While I thank all the panelists, to start with Mr. Kumar for staying on for so long. Thank you, sir, for the support and for staying on for so long and clearly outlining your expectations from not just the study, I think going forward in terms of how the insights need to flow through from not just RISE, but from all battery projects that's being tested on the ground. So thank you very much for staying on. Thanks for continuing to support us all through. Michael, although you dropped out, Michael, thank you very much for, again, your continued leadership on this. We know you've been attending all the webinars that USAID RISE has been putting up. So thank you very much for joining in. The panel members, particularly Dr. Lahiri and Shweta, for staying on, getting up early in the morning and attending this out of the US. So thank you very much for making it convenient. You have been great support on the project. I can testify to that. And we look forward to continued support as the pilots get implemented on ground as well. So thank you for joining in, Sudipta and Shweta. And last but not the least, thank you, Manali, for organizing this and then helping us through in launching a series of webinars. So this was, I hope, useful for the participants. So thank you all. Thanks for your time, and we hope you found it useful. For comments, you can continue to send them across to us, and for questions as well. This is not the end of it. We'll try and answer your questions if we can. So thank you very much. Good night for people joining in from India, and good day for people joining in from US and other parts as well. So thank you.
Thank you.
Thank you. Thank you, Mr. Kumar.